I'm pleased to introduce our very own Mike Adler, Dr. Mike Adler. He graduated from MIT in 1971 with a PhD in solid state physics, and he worked at General Electric for roughly 30 years, helping make our electrical grid work. At GE, he managed a group of 150 people doing research in electronics, power control, and semiconductor assembly. He's widely published and is a fellow in the Institute for Electrical and Electronic Engineers, and for a while he was president of that group. And he was also on the board of directors. Currently, Mike lives in Jackson and does not work for a living. He has lots of hobbies, astronomy, which he spends a great deal of time on. If you unfortunately have medical procedures, you'll see his artwork on the walls at the hospital, the clinic. Every time I've been in there, I've seen his artwork. He has two very nice telescopes, three nice telescopes at his house. And I think he was part of getting the Snow King to put a telescope up on their hill. They're putting a very large one. The dome's already up there. If you go for a walk up there, you'll see it. Since then, he is on the board of Wyoming Stargazing, the Foundation and Friends of the Teton County Library, and Geologists of Jackson Hole. He's given 15 talks to this group, all of them good. And maybe more important to some of you, he's led 4 international field trips that were all a big hit. But I think his wife made him retire from that. So please welcome Mike.
Okay, thank you, John. Appreciate the nice introduction. And we'll proceed with the talk. The title of the talk is A Journey to the Sun. And some of the material that is in the talk comes from the various websites related to the Parker Solar Probe, my own website, Earth and Sky Imaging, where you can look at my pictures if you wish, and as well as Astronomy Today and numerous other publications. So this is the agenda for the talk. We're going to start with an overview of star types. Then we're going to talk a little bit about what the Parker Solar Probe is. You probably may or may not have heard about this. It doesn't get the publicity that some of the other NASA missions do. Then get into the sun details, talking about the solar wind and some of the Parker results. We'll then shift gears and get into life cycle of the star, of the sun in particular, how it was formed and unfortunately how it will eventually die. And then finally some solar phenomena such as solar storms, eclipses, and aurora. So just to ground us a little bit in what stars are, or at least how many there are of them, there's something like 10 to the 21st, give or take an order of magnitude or two, of stars in the universe. And interestingly enough, this is about the same number as grains of sand on Earth, to give you a sort of idea what 10 to the 21st really means. It's also interesting if you're into semiconductors, which I was. This is roughly the number of chips, the number of transistors in all of the chips that have ever been made since 1947, which is what the birth of the very first, the semiconductor industry and the very first transistor. Talking a little bit about our local environment, our solar system, the sun and the planets are in the Milky Way galaxy, which is about 100,000 light years wide. The sun is equally located roughly between the center and the edge of the galaxy. We are one of 200 billion stars in the Milky Way galaxy. And then our nearest neighbor, large galaxy called the Andromeda, belongs to our local group of about 30 galaxies, which will eventually all collapse into a single large galaxy. But this one at the moment contains about a 100,000 billion stars, 1,000 billion stars, which is about 5 times the number in the Milky Way, so it's considerably bigger. It's also about 2.5 million light years away. What that means is that the light that we see from the Andromeda now left the Andromeda galaxy 2.5 million years ago. And remember, this is the closest galaxy, closest large one. In addition, these two galaxies represent two of about 1 trillion galaxies in the universe, to give you a feeling for how large the universe is. And to put a further point on this, Pluto, which is the planet that's most of us think of as being about as far away as anything in our solar system, and of course it's no longer considered a planet. But anyway, it is 5.4 billion kilometers distance, which amazingly is only 5 light hours. And we were talking about 2.5 million light hours to the nearest neighbor galaxy. And it took the New Horizon spacecraft, which was studying Pluto, 9 years to get there. And then if you want to look out a little bit further to our nearest neighbor star, which is about 4.3 light years away, and to give you a feeling of what that distance really means, is if the sun and the earth were only 1 foot apart, this star would still be 87,500 miles away, which is about 3.5 times the orbit around the earth. And then to further put a point on this, we have a spacecraft, the Voyager spacecraft, which has actually is leaving our solar system now and is traveling about 60,000 kilometers an hour. If it was headed for the nearest star, 4.3 light years away, it would take 60,000 years to get there. So people who ask, when are we going to be able to explore the stars? The answer is not anytime soon. Okay, so this graph here also shows the methods that astronomers use to calculate distances or measure distances in the universe. 100 years ago, no one knew how to do this. And there was a great debate about the Andromeda galaxy. In fact, was that galaxy a part of the Milky Way, or was it a separate galaxy? And there was 2 sides to that equation. Well, Hubble put an end to that in 1926 because he used a variable stars. So he found a variable star that, and the frequency of the variable star is proportional to its absolute brightness. This was discovered by a woman, Henrietta Swan Leavitt, who was a Harvard astronomer. She should have gotten a Nobel Prize for this, but she didn't because she died before that was possible. But anyway, this is one of the fundamental methods we use nowadays. And in addition, we use some other methods that even allow us to look further out into, hundreds of billion light years away, using an object which is called a standard candle, which is a supernova, a type 1A supernova, all of which are about the same brightness. So if you know you measure the apparent brightness and knowing the actual brightness, you can figure out from 1/r² relationship how far these galaxies are away. Anyway, just a little bit of background. Now, let's look at stellar brightness. The brightness of stars is broken down into various magnitudes, and I think most of you here are probably at least familiar with that concept. It all started with the magnitude 1, and it was assigned for the brightness of basically the brightest stars in the sky, not including the sun or the moon. Getting to that, and then the magnitude scale continues, and at magnitude 6, this is just about the dimmest object that you can see with your naked eye, and each magnitude is 2.5 times dimmer than the previous one. So 6 magnitude is something over 100 times dimmer. Now, if you look at the sun, the sun and the moon are brighter than any of our stars. It has a negative magnitude of -27. And if you take 2.5 and raise it to the 26.7 power, you find out that the sun is 40 billion times brighter than a first magnitude star. So it's really bright. Shouldn't surprise anyone, but you probably didn't know exactly how much brighter it was. And then the rest of the objects in the sky, like the moon, is -12.5. Venus, which is not a star, it's a planet, is -4.4. And then we get into the brightest stars, which are all close around 1 magnitude. And the Hubble telescope plus other large telescopes, can see out to about a magnitude of 30. And the 1 meter telescope that's going to go on to, or is on Snow King, goes out to about a magnitude of 20. If you want to actually know the actual brightness, which is called the luminosity, you have to know the distance to the star. And so you take the apparent brightness, which is what we measure from the Earth, and then square the distance to it, or scale it that way, and that gives you the actual brightness. Now, talking about stars themselves, the stellar temperature of a star is probably one of the most important features of the star, because it tells us an awful lot about the star itself, because stars themselves emit light related to its surface brightness. For example, a star like Rigel in the Orion constellation has a surface temperature of about 30,000 degrees Kelvin, which I'll tell you, it's about 5,000 or 6,000 times brighter than the sun. And then the bottom of the other bright star in the Orion constellation is Betelgeuse. It has a surface temperature of about 3,000 degrees. And so if you want to know the surface temperature of a star, what you have to do is you measure the wavelength of the star at two different wavelengths, measure the brightness at two different wavelengths. And then the black body radiation has curves for each surface temperature. So by measuring the wavelength at brightness at two different frequencies or wavelengths, you can determine which curve it lies on. So this is the Sirius curve here, 30,000, and this is the curve associated with Betelgeuse at 3,000 degrees. The sun is 6,000. And so this diagram looks a little complicated, but it's extremely useful, and it's quite important. On this graph, on this axis, you have the luminosity, which is the actual brightness on a logarithmic scale. And on this axis, you have the surface temperature. So as I mentioned, the surface temperature is extremely important in telling you a lot of information about the star. So 90% of all the stars in the sky lie on this particular curve called the main sequence of this curve, this plot. This is called the HR plot, which is named after the astronomers who first came up with this concept of characterizing stars this way. So here at 6,000 degrees is the brightness of the surface temperature of the sun. If you look like this up, here's the sun right on the main sequence, and it has unity luminosity. So it's all scaled. Everything on this graph is scaled to the sun. So if we were just talking about Rigel. So if you run up this curve, there's Rigel up here. So immediately you can see that these lines tell you about the size of the sun. So if you know the brightness, you go up and you can find out its size. So we learned that Rigel is 10 times bigger than the sun. And the mass is also shown on this curve, going from 0.2 masses, 0.2 of the 20% of the mass of the sun up to 15 times the mass of the sun. And that's roughly what the size of Rigel is too. So you learn an awful lot of information from this curve by only knowing the surface temperature. Now let's talk a little bit about the Parker Solar Probe. It's, as I mentioned earlier, you may or may not have heard about this. It doesn't get the publicity that like the Mars rovers do, like Curiosity, et cetera. But it's an extremely important spacecraft, and the mission itself is telling us an awful lot about what's going on in the sun. I'm not going to describe this in too much detail because there's a video the next slide will actually have a video that does this, but I will mention some of its capabilities. It can measure solar wind particles, electrons, protons, and alpha particles, which are essentially a group of protons. Then it can also measure electric fields, magnetic fields, and the fields, waves associated with these fields. It can take pictures, so it has quite a capability. So this video is going to tell you a little bit more about the mission.
Parker Solar Probe is not just a spacecraft, it's a dream come true. A dream that started more than 60 years ago when a physicist named Eugene Parker predicted the existence of the solar wind. He was the first to realize that the sun's corona was so hot that it could escape the sun's gravity and create a supersonic flow of plasma that filled the space around the sun. Parker's theory was revolutionary, but it was also controversial. Many scientists doubted him and challenged him, but he was right. And NASA decided to honor him by naming their most ambitious solar mission after him, Parker Solar Probe. Parker Solar Probe was launched in 2018 with a bold goal: to touch the sun. To do that, it had to fly closer to the sun than any spacecraft before, and it had to survive the extreme heat and radiation of the sun's atmosphere. But how did it do that? Well, it had some clever tricks up its sleeve. First, it had a powerful rocket that boosted it to incredible speeds. At its fastest, it can zoom around the sun at about 430,000 miles per hour. That's fast enough to get from Philadelphia to Washington, D.C. in 1 second. Second, it had a thick shield made of carbon composite that protected it from the sun's heat. The shield can withstand temperatures reaching nearly 2,500 degrees Fahrenheit, 1,377 Celsius. That's hotter than lava. Third, it had a smart cooling system that kept its instruments at a comfortable temperature. The system used water to circulate heat around the spacecraft and radiate it away. And fourth, it had an autonomous software that controlled its orientation and attitude. The software made sure that the shield always faced the sun and that none of the other parts of the spacecraft were exposed to direct sunlight. Thanks to these tricks, Parker Solar Probe could fly closer and closer to the sun, breaking records and making history along the way.
So in terms of the mission, the goals for this mission, it has, I've summarized it a little bit here, but it has two main objectives. First is to trace the flow of energy that heats and accelerates the solar corona and the solar wind. And the second part of this is to determine the structures of the plasma and the magnetic fields at the sources of the solar wind. And we'll be talking some more about that, but those are the two main objectives. Now, I'll tell you a little bit more about it. This diagram here shows the type of orbit it has. And as mentioned in the video, it was launched in 2018. That same year, it made its first flyby of Venus, which takes it out away from the sun. And then it had its first perihelion on November of that year, which is the closest passes that it has when it's making one of these orbits. Eventually, it's going to have 24 orbits. One thing I might quickly mention is that, which is an interesting fact, that the probe required 55 times more energy than would be needed to reach Mars. And then the question is, well, why is this? And it has to do with the fact that once the probe has cleared the Earth's atmosphere and has beaten the gravity of Earth, it is still moving extremely fast around the sun. And to be able to orbit the sun, it first needs to slow itself down, and that requires a lot of fuel. And so that's the reason why it takes a large rocket. The Delta IV rocket that launched it is a huge rocket. It's one of the biggest ones we have. Anyway, there will be 24 orbits. It's already into 17 at the moment, and I'll talk some more about that. And that'll also involve 7 Venus flybys. The 17th orbit just happened in September of this year, and but ultimately it's going to get extremely close to the sun. Eventually, starting in December 24, it will begin its last series of orbits, and it's expected to get within 3.8 million miles of the sun and travel as the video indicated. It'll be traveling at 430,000 miles per hour when it does this. This is the fastest speed that any spacecraft that anyone on the Earth, any of us, have made. Okay, so moving along, we're going to show another video here of a little bit more about why this mission is important.
But why do we care about touching the sun? What does it mean for us on Earth? Well, as we said before, we live in the sun's atmosphere. And what happens on the sun affects us here. The solar wind carries not only particles but also magnetic fields that interact with Earth's magnetic field. This interaction can create beautiful auroras, but it can also cause geomagnetic storms that can damage satellites, disrupt power grids, and harm astronauts. The solar wind is not always steady and smooth. Sometimes it can be faster or slower, denser or thinner, hotter or colder, depending on what's happening on the sun. For example, when there are explosions on the sun called solar flares or coronal mass ejections, they can send huge bursts of solar wind towards Earth. These bursts can arrive in a matter of hours or days and cause severe space weather effects. Understanding how and where the solar wind originates will help us predict these events and prepare for them. It will also help us protect our technology and infrastructure from potential damage. But there's more to it than that. Studying the sun also helps us learn about other stars in the universe. The sun is our closest star and our best laboratory to test our theories and models of stellar physics. By touching the sun, we can touch other stars as well. And who knows what else we might discover along the way? The sun is full of surprises and secrets that we have yet to uncover. The Parker Solar Probe is opening new windows into our star and its mysteries. And it's not done yet. It still has more orbits to complete, each one bringing it closer and closer to its final destination, about 3.8 million miles, 6 million kilometers, from the sun's surface by 2025. That's when the Parker Solar Probe will truly touch the sun like never before. Thank you for watching this episode. We hope you enjoyed learning about NASA's Parker Solar Probe and its mission to touch our star. If you did, please give this video a thumbs up and subscribe to our channel for more amazing videos about space exploration. And don't forget to leave a comment below and let us know what you think about Parker Solar Probe and its discoveries. What do you find most fascinating about the sun? What do you want to know more about? We'd love to hear from you. Until next time, stay curious and keep exploring.
Okay, so we know a little bit more about the Parker Probe, and we'll come back to the Parker Probe and some of its results later in the talk. We're going to talk now about the sun itself and give you a little information about what the sun, some of the properties of the sun. It is a medium-sized star. It is by no means a large star. Their largest stars are 10 and 20 times bigger than the sun. Is about halfway through its life of 10 billion years. Sun has 6 layers, and I'll go through those. The innermost layer is the core, and this is where all the heat is generated, and it comes from a nuclear reaction that's generating the heat, and we'll talk about that in a second. The next layer is what's called the radiated zone, and energy is transported through this area by radiation. That's why it's called that. And then you get to the next layer, which is the convection zone, where the heat is being transmitted by convection, like what happens if you have say a hot bar of metal and you heat up one side. It'll eventually the heat will transfer to the other side by convection. And then finally, there is a visible surface called the photosphere, and then you get into the sun's atmosphere, a thin layer called the chromosphere, and then a very large, thick layer, not very dense, however, called the corona. And we never see the corona except during a solar eclipse. The core temperature it was in the diagram, but it's about 15.7 million degrees Kelvin. And the surface of the sun is 6,000 degrees. So it's much, much, much cooler than the core. And then, but what's interesting is that the corona has a temperature of 1 to 2 million degrees Kelvin. So it's much warmer, much hotter than the sun's surface. And that's very interesting, and it's been a puzzle that we think we know the answer to now. We'll be talking about that. The sun itself is mostly made out of the 2 elements that were created when the universe was born. The first is hydrogen, and 73% of the sun is hydrogen. and 25% is helium. And the sun is composed of probably most of the rest of the elements in the periodic table, but all of them together, they only amount to 2%. And all of these other elements were made by other stars, and I'll talk some more about that as well. The size of the sun is about 864,000 miles in diameter, which is about 110 times the size of the sun, the Earth, excuse me. And this gives you some feel for this diagram picture. Here's the sun in the background, and you can see even the large planets like Jupiter. Jupiter is 10 times smaller than the sun, and here's the Earth at a 100th of the size of the sun. So we talked about the nuclear reaction. So the sun generates its energy through what's called a fusion reaction. So we have the core of the star, the core of the sun, is largely made out of hydrogen. And so two hydrogen atoms together with neutrons form a fusion reaction, and the fusion reaction creates helium, creates the element helium with a lot of energy. As it turns out, the helium product of this reaction has 0.7% less mass than the hydrogen that went into it. So what happens to this mass? It's converted to energy and light. And that's, if you all probably remember or heard of Einstein's famous equation, E equals mc squared. Well, that M, that 0.7%, turns out to be a massive amount of energy. And in fact, to put a scale on this, that difference, mass energy conversion, produces a mass energy conversion rate of 4.26 million metric tons per second of energy, and it produces 3.8 times 10 to the 26 watts of energy. This is equivalent to 92 billion megatons per second of TNT that would be exploding to equal this amount of energy that the sun is releasing every second. Turns out if you take all of this energy, but then scale it, divide it by the mass of the sun, or the size of the sun, excuse me, it turns out this is 276 watts per meter cubed, which is about what has the same energy density as a compost pile does. But this is a very big compost pile. Okay, so I also might mention that the density of the sun, if you're curious about that, is about 160 grams per cubic centimeter, which is about 15 times more dense than lead. Okay, so we're now going to trace the path, as to how this energy that the sun is creating in its core gets out from the sun and eventually to us and the rest of the solar system. And the way this first happens is that the energy that's released by the nuclear reaction turns into gamma rays. These are extremely high energy photons, and they're very deadly. So these gamma rays proceed from the core into the radiative zone, but they get immediately absorbed in that and then re-radiated, and then that radiation gets absorbed and re-radiated again and again and again. So finally, when this photons that finally leave the radiative zone, the temperature is dropped to about 1.5 million Kelvin. And then those photons enter the convection zone, and they are the heat is transferred by convection, not by radiation. And then it finally, the heat reaches the surface of the sun, and lo and behold, we have a surface temperature of only 6,000 degrees. So it goes all the way from 15 million in the center to 6,000 on the surface. And I pretty much talked about this fact, just in terms of the size of the radiative zone is about 0.45 solar radii, and the convection zone is out at about 0.7 solar radii from the center. Okay, so here we are at the surface of the sun. As I just mentioned, it's about 6,000 degrees K. It is only about 3,000 kilometers thick, so it's quite thin compared to the the overall size of the sun, and it's not very dense either. It's only as dense as 40. It has the same density as 40% of the Earth's atmosphere at sea level. So, so what happens now is that that 6,000 degree temperature is the temperature by which the sun transfers its energy from the sun to the rest of the solar system, and it does this by black body radiation. And I should have mentioned this earlier when I talked about black body radiation, but if you think about a bar of iron that's been heated very hot, it glows red. Well, that's black body radiation. It's photons, light, that is emitted because of the temperature of the body that it comes from. And this is actually counter to the popular notion. People will say, well, the photons that we see at Earth originated in the core of the sun, and it took taking millions of years to reach the surface. Well, that's not true. I mean, those photons are gamma rays, and if those were the ones that actually reached Earth, we wouldn't have any life on the Earth, because that's extremely deadly radiation. So what is the radiation that reaches Earth? So this is the black body curve. We have irradiance, the light, and as a function of wavelength here. And the yellow curve is the light, is the curve associated with the radiation that's coming from the sun itself, and at 6,000 degrees. So this is the curve for black body radiation at 6,000 degrees Kelvin. When it finally gets to the top of our atmosphere, it has it's a little more jagged, but it's and you can see this curve here is the irradiance that reaches the surface of the Earth, and you can see by the colors that the peak of the curve is around a little less than 5,000 nanometers in kind of the greenish blue part of the spectrum. But you can see the radiation that we receive on the Earth has a distribution of light from all the way from the ultraviolet into the infrared. And there's some chunks missing, and these chunks represent some of the sunlight that's gotten absorbed in our atmosphere. Okay, then now moving on from the surface of the sun to the corona. So the corona is the sun's atmosphere, and it extends about 6.5 million miles from the sun's surface, which is about 15 radii, solar radii. And the flow of plasma outward from the sun into the interplanetary space is the solar wind. And the average temperature of the corona, as I mentioned earlier, is somewhere between 1 million and 2 million degrees Kelvin, but it can reach temperatures as high as 20 million degrees Kelvin. So what is the cause of this? Why is the corona so much hotter than the surface of the sun? And that we'll talk about that next. But the short answer is it's all due to the sun's magnetic fields. And that almost all of the phenomena we see in the sun is related to the magnetic fields. So the sun's average magnetic field is about 1 Gauss, which is twice as strong as the average field in the surface of the Earth, but can be as much as 4,000 Gauss near large sunspots. Here is the and that the magnetic field of the sun isn't just at close distance to the sun. It actually extends all the way out throughout the entire solar system into space, far beyond Pluto. Overall, the shape of the sun's magnetic field is similar to a dipole field, which is the shape of Earth's field. Dipole meaning one pole, one positive pole and one negative pole, and the field lines go between the two. But it is actually much more complex than that. So there's the dipole field, but then there's all these other fields that are much more complicated and vary with time. And we'll talk about that in a second. And you can see these fields in this picture. This is actually a real picture because these shows charged particles, in this case, 8 times ionized iron. that shows up in this particular wavelength that these pictures were taken about. The wavelength of this emission is about 170 angstroms. But you can see these patterns of, and these represent actual magnetic field lines going from one pole to the other pole, but all over the sun's surface. So and now we're going to talk a little bit about the actual what happens over time, because we know that the sun's activities aren't constant, that the solar activity varies over an 11-year cycle. And that 11-year cycle, it varies by, you can see the activity here in this one over here. Look, you can see the detail on it. There's a lot going on, lots of sunspots, and then gradually to much less activity. And then over the end of the 11th year cycle, you're back to a very active cycle. And associated with the activity of the sun is actually the number of sunspots. And this graph here, going all the way back to 1600 to 2000, it shows the density, the number of sunspots over that period, and the peaks are about 11 years apart. But interesting enough, it's not just that that this 11-year cycle is only part of the story. It turns out that after an 11-year cycle, the sun's magnetic field reverses. The dipole, what was the positive pole becomes the negative pole, and what was the negative pole becomes the positive pole. This happens on Earth too, but it over a period of millions of years, whereas in the sun, it happens every 11 years. And one of the questions about, okay, so what determines the magnetic field? How does the magnetic field happen? And if you studied electromagnetism, you'll know that any current that flows in any wire or anywhere creates a magnetic field. So magnetic fields are created by current. So there is a current inside the sun, and the question is, well, where did that current come from? And it is remember that the core of the sun, the middle of the sun, is filled with plasma, charged particles, plus and minuses, electrons and protons. And because of the fact that the sun is not a solid body, it rotates at different speeds. At the equator, it takes 25 days to make a rotation, but at the poles, it's 35 days. And so it's thought that there's a difference in rotation speed is causing a current to develop, and that's pretty much the explanation for how the sun gets its magnetic field. It's a dynamo, and this current is thought to flow mostly in the convection layer, that layer just below the sun's surface. Then over the same period of 11 years, the complexity of the magnetic field varies considerably. And as I mentioned, it's the number of sunspots is proportional, essentially a mark of the complexity of the sun's activities. And these sunspots are regions that are slightly cooler than the rest of the surface. But they look dark if you look at them through a solar telescope, but they aren't dark. They're still emitting a lot of heat. They're maybe 1,000 degrees Kelvin cooler than the rest of the sun. And these are the places where the sun's magnetic field leaves the sun and then comes back to the sun. So this is a picture I took with one of my telescopes. It's actually a solar telescope. And you can see here 2 sunspots, one here and one here. And you can see a very large disturbance. There's quite an activity around these 2 sunspots, indicating that there's a strong magnetic field that leaves one of these poles, one of these spots, and re-enters the other, causing significant churning in the surface of the sun. If you look at the surface of the sun, you can see it's just a hotbed of churning activities. These smaller patterns are created by probably small spots that result in this these things called specules that are called. Also, you see on the edge of the sun, there is a prominence and a solar flare. And there's probably one right here too. It's just that we're looking right at it, so we can't see the three-dimensional shape of that. Okay, so we come down to the question of, well, what causes the heating of the corona, and what is the source of the solar wind? And the scientists, the astronomers, over time, in fact, the actual this goes back. This theory that I'm about to tell you about goes back some years, but has never been really confirmed. But what it's related to is what's called a magnetic reconnection. So first a disconnect and then a reconnect to the magnetic field. So in this cartoon, what we have here is one solar spot and a sunspot and another sunspot, and the magnetic fields go from one to the other. But as you get further away from the sun, these fields start getting actually closer together, and at some point they actually merge and separate, and then the whole mass of the corona that's shown in the upper part of this up here breaks away and forms an ejection, maybe a coronal mass ejection that goes off. And on a smaller scale, just the regular solar wind. And then the rest of the energy that was once magnetic energy in the magnetic field, once the field's lines break, they result in magnetic energy that's converted into plasma kinetic energy and thermal energy. And so that, in fact, is how the corona is heated. It's heated by the disconnect and then reconnecting of the magnetic fields, releasing the energy that's heating the corona. And this diagram just shows the inflow of the magnetic fields and then the outflow of the energy and the particles from this reconnecting event. And you can see this pattern actually in a real picture here. And the Parker probe has allowed us astronomers to understand this whole process much more completely and much more accurately. And it pretty much is confirmed that this reconnection is the source of the solar wind and the heating of the corona. And this is a diagram that just shows some of these field lines where they're not breaking out, but the process of reconnection is going on all at various scales. And as I mentioned earlier, and this process is probably responsible for the small churning events that you see on the surface in this picture and in my own picture. And then you have the larger events associated with these upper the corona that patterns that go out further. And okay, so I'm going to show you yet another video. We have quite a few videos in this. This is going to be NASA's discussion about this disconnect reconnect process that in the corona.
On August 17, 2011, the sun emitted a solar flare. Two of NASA's spacecraft, SDO and RESI, witnessed the event. They saw more than just the flare. They captured magnetic reconnection. Magnetic reconnection is when magnetic fields connect and disconnect, explosively transferring energy. Scientists believe magnetic reconnection drives almost every dynamic event on the sun, including solar flares. While we cannot see magnetic field lines, NASA's SDO can observe solar particles that move along them, tracing out giant arcades of magnetic loops on the sun's surface. Watch the magnetic structure in the background. The cusp flattens out on top. We see reconnection occur as an X shape begins to form and then splits, with half the solar material falling down and the other half escaping into space. A flare bursts from the arcade of loops and reconnection propagates further down the arcade. The observation is verified by RESI data. Resi saw pockets of high temperatures above and below the loops. This signature arrangement indicates reconnection. The two data sets provide visual evidence of reconnection producing a solar flare, and will help scientists understand the role magnetic reconnection plays in these amazing eruptions.
Okay, so this next picture here, so that's a nice description of the reconnection process. This is one of the results of it, a large coronal mass ejection of this of a chunk of the plasma in the corona. And this diagram here shows the intensity of the solar wind, not including these very large ejections, but the solar wind that pretty much is fairly uniform around the sun in all directions. It has a speed on the order of 7,000 kilometers per second. What's impressive also is the fact that every second the sun emits 1 million tons of charged particles, 1 million tons every second. Okay, so we're going to talk about what happens to those charged particles when in this next video. And if I can find it, there it is.
In a new paper published in the journal Nature this week, reveals a groundbreaking discovery made by Parker Solar Probe. It shows that the fast solar wind comes from regions of open magnetic field on the sun called coronal holes. These are areas where magnetic field lines stick out of the surface without looping back inward, creating open channels that allow plasma to escape. Parker Solar Probe also found that these coronal holes are like shower heads, with jets of plasma emerging from bright spots where magnetic field lines funnel into and out of the surface. These funnels are huge, about 18,000 miles across, and have very strong magnetic fields. But how do these jets produce the solar wind? Well, Parker Solar Probe has an answer for that too. It detected bursts of high-energy particles that match the pattern of these funnels, suggesting that they are caused by a process called interchange reconnection. Interchange reconnection is when oppositely directed magnetic fields pass one another in these funnels and break and reconnect, slinging particles out of the sun. This process releases energy and creates pressure and flow bursts that drive the solar wind. The paper shows data from Parker Solar Probe's instruments, such as plasma velocity, ion energy, and magnetic field direction. It also compares the data with computer simulations of interchange reconnection and calculates the energy release rate of this process. This discovery is crucial as it helps us know how and why the solar wind is generated and accelerated. It also shows that Parker Solar Probe has entered the sun's upper atmosphere for...
Okay, so we'll move on. This is another video. This one is quite interesting. Well, they all have been interesting, but this one is a short video, but it's interesting because it actually shows video of the Parker Solar Probe flying through one of these corona mass ejections. And if it was about at 5 million miles from the sun, which is roughly halfway through, or a little bit less, a little more beyond the solar wind, but corona, but it's well within the corona, and it's flying right through one of these. And it was some of the results of this, since it was right there, was able to determine that that the CME ejection was actually clearing some of the particles and dust that was in the corona as it's passing through. So here's this doesn't have any audio associated with it. Nope. Come on. You'll see the intensity here increasing dramatically. As also, this shows the size, gives you a feeling for how close it is to the sun. This is the Milky Way, and this is planet Mercury, by the way, in the field of view. and the probe is moving somewhat in excess of 400,000 miles per hour as it was doing this. Okay. Now we're going to change gears and we're going to talk about the life cycle of the sun. All stars, large and small, formed from a cloud of gas and dust. If they, and I'll talk about the process specifically about the sun, the difference between the life cycle of a large star and a small star is mainly associated with the end of life, where the sun will become a white dwarf and in a quiet sort of a quiet process, whereas a star that's 10 times the size of the sun will actually explode in a supernova, either creating a neutron star or a black hole. And these supernovas can produce as much light as a whole galaxy in a matter of minutes. Okay, so one of the we talked earlier about the surface temperature of the sun, or of a star, the sun specifically, but the other thing about that's really important about the sun is its mass. And this graph here shows data from stars of different sizes, different solar masses, and the luminosity. And both of these are, the luminosity is on a logarithmic scale. And so is this, by the way. And anyway, the curve here shows that the luminosity is proportional to the fourth power of the mass of the star. And if you, one of the important implications of this has to do with stellar lifetime. So the lifetime roughly is proportional to the mass divided by its luminosity. And so if you do that, one of those masses cancel out, you find out that the lifetime of a star varies inversely, like the third power of its mass. So a star that's 10 times bigger than the sun will live 1,000 times shorter life. Or on the other way of flipping it around, a star a tenth of the mass of the sun will live 1,000 times longer than the sun. And you can see the range of stars that follow on the main sequence. So, and I also should mention, because of the fact that we were just talking about the small stars, most of the small stars that were ever formed are still with us, because they burn through their material at a very slow rate, and they may last trillions of years. Whereas most of the large stars that were formed initially when the first stars were formed have long gone, because what happens with a large star, it just burns through its material much faster, and that's why its life is so much shorter. And you can see from this, so it's mass, but it's divided by its luminosity. So these really bright stars really go through the material very fast. And I should mention about these high mass stars, the first stars that were formed after the Big Bang, about 350 million years after the Big Bang, were extremely large stars. There was no other material in the universe at that time other than the primordial elements of hydrogen and helium. And so these stars were mostly hydrogen, and they went through a cycle of burning through hydrogen, and then creating helium, then helium into carbon, and then carbon into oxygen. And this process goes all the way down, and all of the elements are created this way. But all of these, and this is a good thing, because these elements are critical for life to be formed in our solar system. And in particular, we think that the sun is a third generation star, which means that there was 2 generations of these large stars that existed before the sun was formed. So a star would be created, go through a process of living, and then dying, and these large stars explode in supernovas, spreading the particles and the elements throughout the universe. And then this whole part of this remnant turns out to be can be formed into another star, and that would be a second generation star. And the sun our solar system is the beneficiary of all those elements and is why we exist in particular. I'm now going to talk very briefly or quickly about the sun's life cycle. The first is divided into 7 stages that lead from interstellar cloud to a main sequence of star, and the stages from 7 to 14 that go from the main sequence of star eventually into just a piece of charcoal floating in the in space. So all stars, as I mentioned, begin to form from the interstellar media, essentially mass a cloud of gas and dust that gets a process starting with gravitational instability. Something causes the mass to come together, maybe an explosion of another star, and it starts to collapse. It takes a fair amount of mass, though, to create a star, and something on the order of a million Earths worth of matter for a sun-like star to form. So assuming that it actually forms, it follows the sequence that I'm going to get into. Here we are now, about 4.5 billion years after the sun was formed, and the process was going to happen to the sun is gradually going to get hotter and bigger until it becomes a red giant, and then it will stop being an active star, and we'll get into that. So going back to the stage of 100,000 years after the cloud was formed, it has become in this diagram here. So from cloud to 100,000 years, you have what's called a protostar that is roughly the size of our solar system, with a central area in it that is warmer than the rest, and maybe estimate of 10,000 degrees Kelvin. Then it rapidly grows, attracts more matter, and after 1 million years, its core temperature is roughly 1 million degrees Kelvin. And then after 30 million years, its temperature is, gravity is squeezed, and its temperature has risen to 10 million degrees. And this allows hydrogen to start being created, burning into helium. The fusion reaction begins. And finally, after 50 million years, the outward pressure of the heat from the nuclear reaction and the inward pressure from gravity become balanced, and the star enters the main sequence with a core temperature of 15 million degrees and roughly a radius of 1.5 million kilometers. So this seems like a long time, but it only represents 1% of the time of 1% of its life. And this just shows the diagram, the last several stages in this process leading to a main sequence star. Then what happens during the next several billion years, which is, as far as we're concerned, is the future here. The sun begins to get, the core shrinks and it becomes hotter, and the sun expands in radius and becoming more luminous. And after 10 billion years, a fairly dramatic thing happens. It ends into a stage where it becomes a red giant, and increasing in luminosity by 100x, and its size increasing by also about the same amount. And and at the same time, the core temperature finally goes beyond 15 million degrees and reaches 100 million degrees. And this allows helium alpha particles to form another nuclear reaction, second nuclear reaction, to first form beryllium and then ultimately carbon. And this process lasts for another 50 million years. However, a star like the sun will never reach 600 million degrees for carbon reactions for a subsequent reaction to occur, where carbon actually creates another fusion reaction. And so in the case of the sun, as it says, the fires go out. And this diagram here shows the growth of the sun to 100 times its size, and the core of the sun being made up of a carbon ash. And what happens at this point is that the sun oscillates in its size. So this is a radius as a function of time. The sun oscillates in its size, essentially getting bigger and bigger and bigger, but through quite a few change of cycles. And so the core of the sun, this little piece here, becomes what's called a white dwarf. It is not an actual star anymore. It's just extremely hot, though, and it's extremely dense. It's interesting that about half the mass of the sun is in the core at this point, and it's in a size of about the size of the Earth. So, and remember, the Earth was originally 1/100th the size of the sun. So to pack half of its mass in something is extremely dense, and it's limited by something called electron degeneracy, which is how close electrons can get to each other. And but the outer layer of the sun continues to expand, and it emits light through emission, something called emission. The light from the sun, the white dwarf, excites the gases, the hydrogen, say, in the cloud, and it becomes an emission nebula. This graph is somewhat helpful to show the overall process, what happens between the sun's initial formation 4.5 billion years ago, and at this time, it's interesting, the surface temperature through this entire period stays roughly the same, 6,000 degrees, but its size has been increasing. This purple line is increasing and will continue to increase. Because the surface temperature is the same, the luminosity increases pretty much proportional to the surface area because there's just that much more surface emitting light. And interestingly enough, in about less than 1 billion years from now, it's going to reach a temperature where the sun is going to actually burn away almost all the water that's on the Earth. And it's called a runaway greenhouse effect. So this will give a whole new meaning to global warming. And this happened on the planet Venus some time ago, because Venus is closer to the sun. It was once thought that Venus had almost the same amount of water on it that the sun does. But so sort of in the time between life, sophisticated life began somewhere between 1 billion years ago. And if you look into the future 1 billion years, that life will probably be over, because it'll just be too hot on the planet. So to summarize this story, here we have the sun then leaving the main sequence and going through these various stages of stopping the hydrogen reaction and burning helium to form carbon, and then ultimately ending up as a white dwarf. And this is a picture of what's called a planetary nebula, which is the remnants of the part of the sun that has sort of floated away. And this can be quite large. These things can be many, many times the size of our solar system, maybe as much as a light year. So this is a picture of and this is, by the way, it's called the Ring Nebula. This is a picture of a star cluster called M80, and the cluster astronomers have analyzed the stars in this, and maybe as many as 1 million stars, and plotted it on this HR diagram. So you can see the path that actually I was showing you theoretically or describing actually exists in real life, with all these patterns associated with stars in different phases of their life, ultimately becoming white dwarfs down here. So this is a picture of that Ring Nebula that I made, but I made it from data that came from the Webb telescope, and it's quite spectacular. This compares that picture, which again I made it from the data. Since it's from the Webb, it's in the infrared. The red color being about 25 microns, and the blue color being about 5.6 micron wavelengths. This is a picture of the same object that I took with my own telescope, though, here in Jackson. And it took me 84 hours of accumulated exposure to get this. By the way, the Webb only took 4 hours. And you can see the same patterns of material that have left the white dwarf, which is right here in the middle, which doesn't really show up real well in this picture either, by the way, but it shows up quite well in this picture. And these are other pictures of other planetary nebula. This is Messier 27. This is called the Cat's Eye Nebula, NGC 6543. This was a picture I made also of data from the Hubble telescope. This is another of my images that of the Helix Nebula, showing the white dwarf in the middle and the pattern of material in different forms. All of these planetary nebulas look different. They're somewhat shaped in circular patterns, spherical patterns, and that's what astronomers early on, not knowing what they were, called them planetary nebula because they're round. So we're now going into the last phase of the talk. We're going to talk about solar storms, the aurora, and eclipses.
The surface cools and darker sunspots appear. The electrically charged gas is called plasma. The plasma drags the magnetic field further outwards. The magnetic field stretches and twists like a rubber band, and then the rubber band breaks. Several billion tons of plasma is hurled out from the sun. This is called a solar storm. And after 18 hours, the solar storm reaches Earth. When the solar storm reaches our planet, something strange happens. An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
Okay.
The surface cools.
So this is just a diagram showing what actually happens when the solar wind hits the magnetic field, and the solar wind bends around it, and we get this plasma sheath inside the wind, which blows around the planet. This same process goes on with all the planets. The solar wind goes all the way out and plays a major role in what's going on in Jupiter, in Saturn, and the outer planets as well. Okay, so moving on. This is a diagram that shows the current solar cycle that we're in at the moment. This is the sunspot number, and this is time. And this pink area was the prediction for this solar period, this solar sequence. And the data, this other curve is the data showing that the actual activity is greater than it was originally predicted. And we'll see that the maximum is going to occur pretty much a year from now. So this is a picture that I took of the aurora. That was done on the geologist, the Jackson Hole trip to Iceland in 2017 that I had organized. And we're on the North Shore, and you can see the beautiful patterns of the aurora with the nighttime sky or the early evening sky in the distance. I should mention that the actual aurora is not, the light from it is not the light from the particles that from the sun, the solar wind. What's going on is that the solar winds have charged particles ionize the upper atmosphere, and the green color here is emission from oxygen, and the red color is emission from nitrogen in our atmosphere. So what's going on is the charged particles excite the gases to a higher energy state, and then they relax back to their previous ground state, and the process of doing that, emitting light that has these frequencies. Okay, so shifting to one more solar event that we have all experienced here, who lived here in 2017, August 21st. There was a major solar total eclipse of the sun, and this just shows you the path. Now, it turns out there's going to be another eclipse on April 8th of next year. Unfortunately, it's not going to go through Jackson again, but it will go through a good piece of the United States. And just the width of this is going to be about a 4-minute totality period versus what we had in the previous eclipse was about 2 minutes. This shows a little more detail about what's going on. In fact, you can estimate the effect here. We're going to be about somewhere like 45% of totality. So get your glasses out. You'll be able to see the bite in the sun as it's, but it'll never get more than 45%. So down here in Texas and running through the rest of the this path through the Northeast is where the totality will occur. We're planning, Virginia and I are planning to be down in Texas, somewhere around here, to observe that. Hopefully, well, we already are planning to be there on April 8th. So that's the end of the talk. This happens to be a picture that I took on August 17th, 2017, of the eclipse right here in Jackson. And you can see some prominences. And what's a little unusual about this is you can actually see patterns of the surface of the moon. And this is lit up by what's called earth shines. It's sunlight from the surface of the earth being reflected back. And it only shows up because I took this picture with many different exposures. And normally what you see is just a big black hole here. And in my case, you're actually seeing what's going on the sun. This won some awards. And if you go on to Google and Google this eclipse, you'll find a Wikipedia page that has this picture in it. So that's pretty much the talk. And now we'll entertain some questions from the participants, both here in Jackson at the library, as well as in Zoom land. Yes.
What is the end cycle?
Oh, the end cycle. The question is, what is the end cycle for fusion? It's helium. That's it. Helium will convert from from helium. It goes to an intermediate state, a beryllium, and then it becomes carbon, and that's it.
Get up carbon.
Yeah. So, but carbon will be the end product, the ash. It is the ash of the end of the sun.
Usually a star goes out through the elements.
Okay.
Energy.
I'm going to give another talk at some point about bigger stars and black holes and neutron stars and good stuff like that. But I can tell you the answer is it goes all the way out to iron. And what reason when you get to iron, the same thing happens. Iron core has just been made. It gets squeezed and it heats up. But it turns out the next heavier element takes more energy. It has more energy in its nucleus, not less energy. And so it actually would take energy in. So the fusion reactions are over. So what happens is gravity doesn't know this. So gravity is squeezing and squeezing and squeezing. And eventually what happens is a supernova. And all the heavier elements get created during the supernova. beyond iron.
So we do have a couple Zoom questions.
Okay.
But these remote mics aren't working. I hope everybody on Zoom can hear me. One question, well, Mike, I'm just gonna.
Let me look at it. Yeah, okay.
I'll look at this.
Hi, Mike.
Just
Okay, here.
start-
Question, please talk a bit more about the coronal mass ejection clearing out dust and photons from immediate, what is the source of the dust? This is the corona. It's all a part of the atmosphere in corona. So most of what's corona are charged particles, but there is some dust because the sun. Remember, the sun is a third generation star, so it's not just hydrogen and helium, and but it apparently. And I just read this myself yesterday, so I don't know the details. But in the process of it coming out, it does clear it out. And I should mention that these things are very focused, and the one that the Parker went through was a very large one, and it would have been devastating had it hit the Earth. But these things are focused. They're just, it's like a shower head, and they shoot out, and it missed us. But it was apparently would have been close to the biggest solar storm to ever hit the Earth, but it didn't because it was pointing in the other direction, which was good. Yeah. Yeah. What creates the, what creates a solar magnetic field is the question. And it was on my view graph, but I jumped over it. There's two things, there's two theories about it. First thing is that the sun is not a solid body, and it rotates at different speeds. So at the radius, at the equator, if you want to call it that, the sun takes 25 days to rotate, make a single rotation. On the poles, it takes 35 days. So there's a differential in this spinning, and so that creates currents inside the sun. And it's those currents, and it's thought to be in that next to outer layer, the convection zone, is where what's called a solar dynamo, which is this motion of charged particles in the convection zone, creates the magnetic field. Now, there's another theory which is more or less dismissed, but it's kind of interesting because Jupiter takes 12 years to go around the sun. That's very close to the 11-year cycle. So there is some thinking that maybe Jupiter has a role in this too. So,
they determine the dimensions, the core and the other layers.
I think a lot of it is modeling, and in terms of just the heat generation by the process of the fusion reaction and how big it would be, and I think the density gets less and less because as I remember, we're talking about something that at the surface is less dense than our own atmosphere, the outer layer, not just the corona, the photosphere is 40% as dense as the outer layer at sea level on Earth, the air. So but I think the density in the remember in the radiant zone, the biggest part of the sun is about lead. It's plasma, but it's about the density of lead. Yeah. A lot of lead though, a lot of mass there.
Say, Mike.
Yes.
How is the temperature in the corona measured?
Yeah, well, there's probably lots of ways in which Earth-based telescopes do this, and they're undoubtedly looking at radiation and looking at the radiation from these just the brightness, the temperature from the brightness. What?
Repeat the question.
Yeah, I'm sorry. The question was how is the measure of the, and I'm not an expert on this, and so I will I'm guessing, but I'm assuming it has to do with measuring the actual brightness of the light of the plasma.
So another quick question is, if we have a major solar event, what will be the effects on Earth?
Well, there have been major solar events. There was one that was 100 years ago in the 1850s. There's a name for that. Carrington event. And there wasn't much electronics going around at that point, but it did mess up telegraph. So it did have an effect. It would have a much larger effect now.
Like what?
I have no idea. Well, you know, like knocking out communications. And in fact, that happens, that it has happened. Smaller events have caused disruption in communications. Yes.
What's going to happen to Parker's solar probe once they complete it?
That's a good question. Whether they'll plow it, you know, like they did, the question is what's going to happen to the solar probe once it completes its number of orbits, whether it will do what Cassini did, which is fly into Saturn, whether they'll fly the probe right into the sun. That would be interesting. I haven't read what they're going to do about that, but that is a possible, you know, get even closer, figuring, well, we've got all the data we can get at where it is, so we'll just go closer. I wouldn't be surprised. I don't know that they've figured that out. They haven't publicized that, but let's put it that way. They may have figured it out. They probably have talked about it, I'm sure. Yeah.
Mike, you talked about studying third generation stars.
Yeah.
And how do you get to the third generation?
It's an estimate. It's an estimate. Well, how does it get there? It gets there because there were two. I'm sorry. I should know better than not to repeat these things because I'm supposed to review. I often run these things. Okay. So the question is, how did the sun get to be a third generation star? I think that's the question. Yeah. And the answer is there were two generations of stars before that ended up maybe supernova. But these are stars that ended their life, that were created earlier on remember what I said about the largest stars that were created in the early universe. They were huge. In the process, these large stars would have created all the elements in the chain because they're monstrous stars. They would have worked their way all the way out. They would have created supernovas and blasted all this material, all these elements, the heavier elements, out into the universe. And then another star, this cloud of, you see, you know, when a supernova happens, it leaves a remnant of gas and dust, and some event could cause that remnant to squeeze back again and create another star. And so this has happened. The estimate is it's happened twice before. So it's two generations of stars have come and gone, but in the process of coming and going, they've left a legacy of all these heavy elements, which is why. And so that's also an interesting, if you think about it a little bit, you realize life in the universe couldn't have begun too early because it would take, no matter what kind of life it is, it's not likely that life would be created out of hydrogen and helium. And so it takes these other elements. So you had to go through several generations of stars before any form of life would probably be possible. Yeah.